Hey everybody, thanks for checking out the channel. Some of my viewers asked if a scale RC CV joint, that's a constant velocity joint, are truly constant velocity. And some suggested that they might not be, that they may not truly transfer drive torque at a constant velocity. So let's find out. On this channel, we look at the science behind our grown-up toys. Before watching this video, I highly recommend watching my video on drive shaft phasing so you fully understand that traditional universal joints do not pass torque from the input shaft to the output shaft with a constant angular velocity. The output rotation actually speeds up and slows down during the course of a single revolution. CV joints were introduced to RC over 40 years ago by MIP, created by the founder Eustace Moore, who still runs the company and manufactures in the US to this day. I haven't measured this myself, but I'll take the word of Adam Drake, one of the most successful racers, who explains on his YouTube channel, and I'm sure many others have explained it as well, that CVs have more friction within the joint itself. So, under power, it resists movement more than a U-joint, meaning it feels like your shocks are stiffer because the suspension is harder to move against the friction of that CV joint under power. This really only applies to A-arm style independent suspension and not so much to solid axle crawlers. You might also see the term CVD or CVA. That simply calls out which end of the drive shaft has the spherical part of the joint, the axle or the drive shaft, because RC CV joints are not symmetrical like U joints. However, both CVD and CVA perform the same and are considered CV joints. If you look at a full-scale CV joint, they are quite complicated compared to an RC design. So let's take a look at a typical RC CV joint. The best MIP joints have the axis pins held together with a set screw. However, the assembly can be held together by a clip, a sleeve, a coil of wire, or even an O-ring. This makes them rebuildable, which is good because many people report that CV joints are less robust than traditional U joints. On most universal joints, the cross pins are permanently pressed into place and they don't come apart. I've tried. RC CV joints have an input shaft and an output shaft. It's kind of a spherical ball and socket. The ball half and the socket half could be reversed and it would perform exactly the same way. It's not symmetrical left and right like a U-joint. There is one smaller pin passing through a slot in the sphere, and the socket, or the cup drive shaft, pivots around that axle. Then there is a second short axle inside the ball that rotates within the ball. These axes intersect in the middle and are coplanar, meaning they are simply on the same plane. This axis configuration is exactly the same as a U-joint, just a slightly different way of getting there mechanically. Side by side, you can see they both have the same perpendicular coplanar axes that intersect dead center in the shaft's center lines. So my guess is that the rotation of a CV joint will be non-uniform, same as a U-joint is non-uniform. Let's start by looking at the working 3D model I built based on this RC CV geometry. So here's the RC style CV joint that I built. And you can see one side is a spherical shape, and here's the two axes that the output shaft rotates around. Now let's exaggerate this angle so we can better see any non-uniform rotation on the output shaft. Let's put 50 degrees. That should exaggerate it nicely. So don't worry about this intersection here. The software is just going to ignore that because I told it to and only focus on the rotation about the axes. All right, so I'm driving the input shaft at a very constant rotation. And let's see what's coming out the other end. You can see that it goes slow, fast over the top, slow, fast, slow. Let's exaggerate this some more and see what happens. it'll probably actually run at 70 degrees. So let's see what happens. All right. Now this couldn't really exist in real life, but the computer's smart enough to only pay attention to the parts that I tell it to. And let's animate this and see what happens. There we go. Very constant input on this end and an exaggerated non-uniform output on this end. This is exactly how a universal joint acts. So let's take a look at a U-joint. You probably saw this in my other video. I've got this set to 70 degrees, and let's animate this. And this is the input side. You can see it's moving at a constant input, and the output is speeding up, slowing down, fast, slow, fast, slow. Here they are side by side. Now let's look at how a full-scale CV joint works. There are several different ways to architect a true CV joint, but the Shreppa joint is the most common and was invented by a Ford engineer in 1926. You'll often see this coupled with a tripod joint, which is a CV joint that also slides. And that's often necessary because the length of the drive shaft may change based on suspension movement. So here's a real CV joint that I modeled, and it's exaggerated a little bit from what you might see in real life, but it's basically got this center plane that has the driving balls on it, and these balls roll in slots, and those slots are both in the input shaft and the output shaft so that they can translate relative to both input and output drives. So I'll hide just the output shaft, and you can see there's this spherical shape, and there's these balls that roll back and forth in each of these slots. And there's matching slots on the output shaft. And typically on a real-life CV joint, you might see a cage that keeps these balls lined up on the same plane. I just constrain them so they'll be on the same plane to make it simpler to view. But you'll usually see an additional part in here. And I just did 3 balls for simplicity. Usually there's, 6 or 8 or more balls because these balls carry all the load from the input to the output. So these are critical structural members in the whole assembly. So let's animate this and see what happens. All right, what you can see is that the balls are actually rolling side to side on both members simultaneously. So in a traditional universal joint, you've got this imaginary plane, and the spider or the cross journal flip-flops back and forth along that plane. And that flip-flopping is what gives the non-constant output to the output shaft. Whereas in this case, the balls stay on this plane and they slide back and forth in each of the drive shafts. And that's what allows torque and speed to be transferred uniformly. So let's speed this. Let's take a closer look at this. The input shaft, this is what I've animated. Looks like it's turning very uniformly. And if we look at the output shaft, also moving very uniformly. You don't see that pulsing from before. You don't see that speeding up, slowing down. Now let's exaggerate the angle more and see if it makes any difference. Let's try 75 degrees, see if that'll work. All right. There's obviously some volume interference here, but again, the software will compensate for that and just ignore any volume interferences in areas that I didn't specify that it needs to be constrained. So, wow, let's see if this actually works. This clearly wouldn't work in real life, but in a computer simulation, we should be able to get it to work. All right. So those balls These balls actually want to move in much longer slots than I've modeled, which is funny. But they are constrained correctly, so even though it might look physically impossible, it is constrained to produce the right result. And if we look at the input shaft, constant velocity, and even at 70 degrees, the output is still completely constant. And that, my friends, is the magic of a proper CV joint. Now let's confirm this on an actual 10 scale RC crawler with a little help from some Legos. So let's do a test here. On this side, I have a traditional U-joint, and on the other side, I have a CV joint. And so I've devised this little adapter with a Lego gear on it, and that will allow us to use the card trick to audibly listen to the change in rotation. Now, something interesting is that this is a portal axle. So the U-joint is up here, and this portal has about a 2-to-1 gear reduction in it. And we verified in my last video that a U-joint is in fact not a continuous velocity joint. The output is a non-uniform rotation. So for every rotation in, the output speeds up and slows down twice each. Faster, slower, for one revolution. And because there's a 2-to-1 reduction here, that means you're going to have 4 fast and 4 slow spots on the output drive at your wheel. Because one rotation here at the wheel is half the rotation of the input at the drive shaft. That would make a great video to explore another time. Let's start by measuring the U-joint half and see how much the non-uniformity changes with steering angle. Okay, so I've got my radio locked. We'll try to measure it with this extra mic. What we're hearing here is just some wobble in this axle and this gear. But let's give it a big turn and see what happens. Remember, this is slowing up, this is speeding up and slowing down 8 times per revolution. Can you hear that? And it gets worse the more angle you put on it. Hopefully you can hear that wah, 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 wah. That's the non-uniform rotation, fast, slow, 4 times per revolution at the output. Now let's try the other side. This side, remember, is the side with the so-called CV joint. Like I said, there's a little bit of irregularity coming from just the wobble in the axle and the gear. Now let's try it at an angle. So there you can see it makes the same non-uniform buzzing noise that the U-joint did. Well, I think that demonstrates that this alleged CV joint exhibits the same non-uniform rotation at a steering angle that the U-joint did. If you're looking at a CV joint in the RC universe that's constructed like this, it's not a true constant velocity CV joint. It's just a universal joint disguised to cosmetically resemble a real CV joint. They don't act like true CV joints at all, but they may have other benefits like rebuildability and suspension tuning. I did find a few companies who have attempted to make a real Shreppa joint for RC, but I couldn't find anything current. If you know of one, leave it in the comments.